Hello and welcome to the Solar Wind Magnetosphere Ionosphere Interaction tutorial session. My name is Austin Brenner. I'll be introducing the speaker today. And co-moderating with me is Rachel Rice.
Hello, I'm Rachel Rice. I'm a final year graduate student at Embry-Riddle Aeronautical University, and I'll be fielding questions, so go ahead and drop those in the Q&A section whenever you have them for David.
All right. Our speaker today became an AGU fellow while at the Applied Physics Laboratory, receiving the AGU Maestlin Award in 1992. He actively participated in the Czech, Russian, and Slovak Prognoz and Interball spacecraft programs, ultimately receiving a medal from Charles University in Prague for his services. Upon moving to NASA Goddard in 2002, he served a 2-year term as Deputy Program Scientist, setting up and running the Living with a Star program. His work as project and mission scientist has focused on the Themis Artemis Explorer and the Living with a Star Van Allen probe missions. He is the TRACER's mission scientist. In recent years, he has taken on the leadership of a cross-disciplinary group, prototyping a wide field of view soft X-ray imager with applications for solar wind magnetosphere and solar wind planetary applications. Nevertheless, community service and research remain at the core of his interests. He is a past president of AGU's Space Physics and Astronomy section, and of course, he has held a position as one of the GEM Steering Committee chairs from 2011 to 2013. Without further ado, I'm pleased to introduce Dr. David Sibeck.
Thanks very much. It's a pleasure to see all of you here this morning. Let's see if I can get my screen to show. Okay, I think you're seeing my screen now. I hope you are. If not, let me know. Today, I'm going to talk to you about Dayside Solar Wind Magnetosphere Interactions, and I hope to give you a sense of the enthusiasm which this field of research can generate. So we're going to be looking at the day side of the Earth's magnetosphere, and I'm going to begin with some motivation for studying this topic, and then we'll go through it region by region, perhaps looking at some of the highlights or most interesting things, at least in my opinion, for each region. And then we'll have a brief summary at the end looking forward, because the future is equally bright for those who study this part of the Earth's magnetosphere. There are many exciting missions coming along. So one reason for studying the physics of the Dayside magnetosphere or the Dayside interaction is because you're interested in fundamental processes. And one of those fundamental processes is particle acceleration. That certainly occurs in and around the vicinity of the bow shock and worthy of study in and of itself because of its basic nature to plasma physics. Another basic phenomenon that occurs in this region of space is reconnection. It occurs at the magnetopause, but it also occurs in the magnetosheath and perhaps even in structures upstream from the bow shock. Yet another fundamental process, one that magnetospheric physicists, at least Dayside magnetospheric physicists don't think about too much, is ion-neutral interactions. And they most definitely do occur on the Dayside between the Earth's exosphere and between the solar wind plasma or the magnetospheric plasma. And so that's yet a third reason for studying the Dayside, is a third basic interaction that goes on. And these are themes that will run throughout this talk, and so I'll harken back to them periodically as we progress. Those aren't the only reasons for studying Dayside magnetospheric physics. You can perhaps think of some of the unique features of heliophysics that are very well expressed in Dayside interactions. One is the cellular nature of plasma structures. There are vast regions of space with rather uniform characteristics, and they're delimited by rather sharp boundaries where very interesting things happen. And those sort of things certainly happen. Cellular structures present in the solar wind and the magnetopause and the bow shock are examples of very sharp structures. So it's very common. It's a unique feature of our discipline, one that other disciplines don't have. Teleconnections is another unique aspect of our subject. Who would have imagined, if you look over here at the right, that a burst of reconnection at the magnetopause could excite something interesting happening far, far away, many tens of Earth radii away in the Earth's ionosphere. Teleconnections are real in our subject. In other subjects, they're open for discussion or don't exist. But in magnetospheric physics and heliophysics, teleconnections are common occurrence. Things happen remotely at a great distance. Cross-scale interactions, another unique feature of our discipline. Things that happen on the tiniest of scales, on electron gyro radii, like reconnection at the subsolar magnetopause, can ultimately lead to a complete reconfiguration of the Earth's magnetosphere, placing boundary layers and plasma regimes in different places, changing the size and shape of the magnetosphere. All of these are good reasons and fascinating topics to study in Dayside interactions. Yet another reason to study Dayside interactions is the key role that the Dayside interactions play in the system science of the magnetosphere. The energy that powers geomagnetic storms and substorms, big space weather effects, originates in the pristine solar wind, but is modified, diverted, and are focused to enter geospace by crossing through the Foreshock and Bowshock, passing through the Magnetosheath, entering somewhere across the Magnetopause and down into the Cusps, and flowing down all the way down to the high latitude Dayside ionosphere. So by studying what's going on in each of these regions, which I've numbered here and which we'll be talking about during this talk, I can learn a bit more about the nature of that interaction, either in situ or remotely. So I'd like to start where it all begins for the magnetosphere, at least for the majority of processes in the magnetosphere, and that's in the solar wind. And why should we study the solar wind? Well, it's a driver for many geospace phenomena, for example, storms and substorms. There is a great review article by Joe Borowski, which I would like to refer you to. What I have time to talk about today a little bit is the solar wind at solar max and solar min, and the control parameters that it exerts on the magnetosphere, and triggers in the solar wind, and how confident we are or how unconfident we are about whether they come to the Earth. This beautiful picture on the right shows the kind of cellular or spaghetti structure of the solar wind as illustrated by Joe Borowski in that article. So here are two plots showing various solar wind plasma and magnetic field parameters. On the left is solar maximum, on the right is solar minimum. What you get is a full year of data in both cases. And you might initially say, well, gee, they look about the same. What's the difference between solar maximum and solar minimum? And the answer lies in the scales of these plots. Just all of these features, the variations in magnetic field and in plasma parameters are just so much bigger in solar max than they are in solar min. So that's solar maximum. You've got very strong drivers for magnetospheric phenomena. And I've put this in because I want to contribute this talk to a permanent record. It shows you histograms of solar wind parameters during solar wind and solar maximum and solar minimum, and it shows you averages and standard deviations, but that's not the key point. The key point which I want to talk about is just about anything you can think of in the solar wind is for some phenomena in the magnetosphere, and we're going to talk about those today. For example, the spiral or orthospiral or some other orientation of the IMF, that determines where the foreshock is. The north-south orientation of the IMF can help you determine where reconnection occurs on the magnetopause. The electric field in the solar wind might determine the strength of the interaction. The velocity of the solar wind might tell you whether the Kelvin-Helmholtz instability will occur on the magnetopause. The shock numbers in the solar wind determine the shock location and strength. Plasma beta might inhibit reconnection. The flux of solar wind ions is a key parameter determining how much charge exchange with exospheric neutrals goes on. The solar wind dynamic pressure tells you where the magnetopause is, and the ratio of heavy ions to protons has an important factor in determining where X-rays are generated. We'll talk about these all a little bit more in future. This sort of gives you a guide to where I'm headed. So solar wind input really matters. It may come as a surprise, but there are still people alive today who remember a time when there was no L1 monitor. That was pretty difficult. You didn't know what the input was. Nowadays, you can always find L1 observations. In fact, confusingly, sometimes you can find L1 observations from more than one spacecraft, and it's difficult to know which one to use. And before we get underway talking about the magnetosphere, I'd like to see just how confident we can be when you take these L1 monitors to determine the magnetospheric response. And we'll look on 3 timescales: geomagnetic storms, a timescale of days; substorms, hours; and looking for triggers for flux transfer events and substorms on a timescale of minutes. So it may come as a surprise to you, but L1 monitors are not usually directly upstream of the Earth along the Sun-Earth line. They follow these kind of circular paths, hovering around the L1 libration point upstream, and they spend most of the time, let's see if I can find the point, they spend most of the time way off the Sun-Earth line, as this histogram of position shows. If they were right on the Earth-Sun line, they'd be here along this dashed line. Usually they're far off that dashed line. So they might not see what you want them to see coming to Earth. Let's go back. There we go. Okay, so on storm timescales, you're pretty safe. Why would I say that? Because there are these different models predicting the occurrence of geomagnetic storms, and for any given solar wind input, they kind of get the general sequence of DST right, which means that they're getting the storm prediction correct. The differences probably depend on the model rather than any problem with the solar wind input. So over long timescales and for big events like geomagnetic storms, no trouble with your solar wind monitor. How about on hour timescales? If you're looking for an hour or two of southward IMF orientation to see if there'll be a substorm, will you get it? Well, it's pretty good, as this correlation trace between wind and ACE shows. BZ is pretty well correlated on hour averages. But there are some problems if you look a little bit closer. You might think, based on wind observations, that IMF BZ is 0, when ACE says it was plus or minus 4 nanoteslas. Maybe that's okay. Maybe you don't mind that. How about on minute timescales? There, the scatter looks even worse, big scatter. Now, if you think the IMF is plus 10 nanoteslas, in general, from one spacecraft, the other spacecraft says it's also about plus 10 nanotesla. But how about if you thought it was 0? There's a big spread in what it might really be if ACE is the one that's really seeing what the input is, and wind is the one that is what you think the input is. Maybe those discrepancies bother you. Maybe they don't. I don't know. How about correlation lengths? Here, plasma and magnetic field parameters have been correlated over different scale lengths in the solar wind on using minute data, and the correlation coefficients are only 0.6 to 0.7, which means you're only explaining 36 to 49% of the solar wind variability. So if you're looking for a solar wind trigger and you're using a monitor at the L1 libration point, there's a good chance you're going to miss it, or you're going to pick something that didn't really come to Earth. It's a risky business. These are the scale lengths for solar wind features that were derived by Richardson and Paularina in this study. And these distances are comparable to those that L1 monitors lie off the Sun-Earth line. Okay, let's move a little bit closer to the Earth. Why did we study the foreshock? It's a great place for particle acceleration. And as I'll show you, it dramatically modifies the incoming solar wind. So if you're a magnetospheric physicist, please think about what happens to the solar wind in the foreshock. And I'll show you that in a few slides. Where is it usually for steady state? For spiral IMF orientation, it's usually upstream of the dawn magnetopause. We're going to look a little bit at particle distributions in the foreshock and the waves that are generated there. And we're going to talk a bit about how it modifies the incoming solar wind. So here we go. Particle acceleration in the foreshock. It might be a good investment for you. You stick in 1 keV solar wind ions, or perhaps a little bit higher energy ones, as seed population, and out pop back up to 1 MeV, maybe even greater energized foreshock ions. So something in the foreshock at the bow shock is doing a great job of accelerating a small part of the incoming population. Processes that could occur are specular reflection off the bow shock, Schafter acceleration, or diffusive Fermi acceleration. Good review by Dave Burgess in 2012. And a small fraction of those incoming ions and electrons really do get energized. We now have global hybrid code models that can predict self-consistently the particle distributions. in particular the Glaciator code in Finland, but other codes are available, showing incoming solar wind and Foreshock ions, really cool, and how they interact with each other via waves to produce diffuse or other types of distributions in the Foreshock. What does the Foreshock do for the magnetosphere? Well, amongst other things, it generates waves by interaction of solar wind ions with reflected ions. And it bathes the magnetosphere in those energized particles. And here's an old figure showing which regions of the magnetosphere lie behind the quasi-parallel bow shock, that is the regions to which these waves or structures or particles in the foreshock can reach at the magnetopause. So these global simulations can actually be used to predict the waves in the sheath. Some of the waves are generated in the foreshock like here. Others are mirror mode waves generated in the magnetosheath. The magnetosheath and the foreshock are just full of waves that are going to impact the magnetosphere. And here's a recent run comparing observations with simulations of those waves being generated in the foreshock. I can't find my pointer. In the foreshock and propagating through the sheath and getting into the magnetosphere. Cool stuff. Whoops. Okay, these waves and the energized particles, they're not negligible if you're a magnetospheric physicist. Sure, those energized particles in the foreshock are few in number. They're not that big a percent in density of the solar wind population, but they're energetic and they have a high temperature, and therefore they exert a large pressure on their environs. And what happens is they excavate giant diamagnetic cavity in the magnetic field strength and density. Here's an example, a burst of Foreshock ions, and it's excavating a cavity in the magnetic field strength. It's excavating a cavity in the density in the Foreshock. And that it's the excavated properties, it's the modified solar wind that's actually going to come and hit the magnetosphere. So it's important to know about that. How big of an effect could it be? Well, here's a paper that says during a period of radial IMF, the magnetopause expanded 3 Earth radii outside of its typical position. Well, that would be an 80% decrease in solar wind pressure. So this is a big effect. The foreshock should not be ignored. And you'll ignore the foreshock at your own peril if you're seeking to understand the solar wind magnetosphere interaction. It generates big pressure changes on the magnetosphere, sometimes localized, sometimes global. There are a lot of wild animals. This is a very recent years have been a prolific time for studying transient events that are generated in the foreshock. Some of these transient events are generated when IMF discontinuities strike the bow shock, hot flow anomalies. Some are generated by IMF discontinuities entering the foreshock. Some are located between IMF discontinuities. Some of them occur without discontinuities. These events upstream in the foreshock have their own local transient big effect upon the solar wind magnetosphere action, and in particular upon the magnetosphere. Here's an example of one, and perhaps it doesn't look too impressive to you. There is a hot flow anomaly hiding in this figure. You can kind of see it by the bumps in magnetic field strength and density and the big deflection in flow, which makes it a flow anomaly. But perhaps you're not impressed by that. You think that's just a wiggle. But look what it does to the magnetosphere. Those sort of events can drive 5 RE amplitude waves on the magnetopause boundary. That's pretty big. And those waves propagate anti-sunward with the solar wind. Big effect. Magnetosheath. Why should we study the magnetosheath? It provides outer boundary conditions for the magnetosphere. It's a place where ion-neutral interactions readily enable remote sensing of the boundaries and plasma characteristics of the magnetosheath, and it happily transmits and generates new interesting structures and waves that move from the foreshock through the sheath to the magnetopause. Where are we now? Wonderful statistical studies of magnetosheath plasma and magnetic field parameters exist. There are missions in the past and in the future to remotely sense the magnetosheath. Those who love waves find it a wonderful place to study various types of waves, and there are very interesting transient events that occur in the sheath. Let me summarize those. Here are just some of the beautiful pictures that have originated from work presented at GEM and done in the past few years. These pictures on the right showing statistical patterns of plasma parameters in the magnetosheath, in the outer magnetosphere, are just a fantastic way to visualize the solar wind magnetosphere interaction. When you look in details, sometimes you find striking dawn-dusk asymmetries in the various parameters in the magnetosheath. Lots of physics to learn from those. Ion-neutral interactions. The magnetosheath is a place where solar wind plasma meets exospheric neutrals. And when that happens, they often exchange electrons. And when they exchange electrons, the solar wind ion goes shooting off as an energetic neutral to distances far away, enabling remote observations. Some of the most spectacular results seen at the GEM meeting and seen in the past few years come from IBEX observations of ENAs. You can actually remotely sense the inner and outer boundaries of the magnetosheath from energetic neutral atoms seen many tens of Earth radii away. You can remotely sense the cusps, another topic that we'll come to in a few minutes. And in more recent years, there's been a lot of effort generated towards remotely sensing the magnetosheath in soft X-rays, because when high charge state solar wind ions meet exospheric neutrals, they also exchange electrons, and that exchange of electrons can result in the emission of soft X-rays. There is as yet no wide field of view camera looking at the magnetosheath to see these emissions, but narrow field of view astrophysics missions have seen them on multiple occasions. They're always there, and ultimately, when such a mission flies, and such a mission is scheduled to fly, as I'll talk about in future, we will be remotely imaging the sheath in soft X-rays too, and the cusp in soft X-rays. What about waves in the magnetosheath? Spectacular simulations coming out from global hybrid codes. You can see mirror mode waves throughout the dusk side magnetosheath generated by temperature instabilities. Over on the dawn side, that's a more likely place for Foreshock waves to be transmitted through. The temperature anisotropies that you need to generate the waves are there. The beta is what you'd expect. There are also bow waves that encircle FTEs as they move along the magnetopause. Here's an FTE that's moving, and here's a bow wave that it's sending out in front of itself as it moves poleward and northward. The magnetosheath is an interesting place to study for those who like magnetic reconnection. The interaction of a tangential discontinuity with the bow shock may compress the discontinuity, squeeze it, turn reconnection on. And here's a paper by Taifan showing the reconnection jet, showing the electric fields with plasma moving in, and showing that this was a tangential discontinuity. Cool phenomenon. Transients, all of those features I mentioned in the Foreshock region, they're transmitted through the magnetosheath. Here's an example of one transmitted into the magnetosheath reported by Shafrankova et al. This is a hot flow anomaly from the upstream region pushed through the bow shock and transiting the sheath. So you have every reason to believe that that's going to ultimately come to the magnetopause. And a pet peeve at the bottom, a lot of journals are archiving themselves in black and white, and you can see what that does to color spectrograms. Bad idea. Also, new features in the magnetosheath, features that were not present in the upstream region, that were not in the foreshock. So the sheath is a veritable zoo of transient events that are coming towards and about to smack the magnetosphere. One example of those are magnetosheath jets, as proposed by Heliophysics at a GEM meeting. She was a regular GEM participant. And what happens is there are ripples in the bow shock, and those ripples launch high-speed jets, which propagate into the magnetosheath. Fantastic picture of that happening over here from Karima Badi. Jets are moving along streak lines through the magnetosheath, and they're moving so fast that they have a bow wave in front of them as they approach and strike the magnetosphere. Cool, really cool. Finally, the magnetosheath is a loss region for magnetospheric particles. One of the most fascinating simulations I've seen in the past number of years comes from Karim Soratia at JHU APL. He launches blobs of protons and oxygen and electrons on the night side and watches them drift around the magnetosphere. Some of them succeed in traversing the dayside magnetopause. Others go smack into the magnetopause, and those particles are lost to the sheath. Very interesting to see where and when they're lost and where they go. Magnetopause. Why study the magnetopause? It's a gateway for solar wind energy to enter the magnetosphere. It's a super place to study reconnection physics. There are an abundance of transients there. The sort of things we think we know, but do we really? Or where is the magnetopause? And the sort of things that are hot topics right now, are, as always, are transients and flux transfer events and the Kelvin-Helmholtz instability. Do we really know where the magnetopause is? Here is an old paper from Shu, 97, comparing their predictions of where the magnetopause is for solar wind dynamic pressure and BZ with those that Roloff and I got many years ago. Sometimes the predictions are similar, and sometimes they are strikingly different. Look at these two panels. This panel here should look like that panel there. Obviously, there's a gross discrepancy. What we usually try to do is determine the magnetopause location using hourly average solar wind parameters of the solar wind dynamic pressure, IMF-BZ, and sometimes dipole tilt angle. But since the magnetopause lies at rest where magnetosheath and magnetospheric pressures balance, and magnetospheric pressures are mostly magnetic, and magnetic pressures are due to magnetic fields, and magnetic fields are due to currents, it might be better if we were looking at magnetopause locations as a function of the Chapman-Ferraro current strength, or the region 1, so the ring current, or the cross-tail current. And all of those have different response times to solar wind variations, ranging from minutes to hours. So it's a complicated business, and you've got a lot of work to do if you're really going to predict the magnetopause at any given time. Here's an illustration of the ring current. Ring current enhances magnetic field strengths in the outer magnetosphere. The cross-tail current depresses them. The region 1 currents depress them. They're all varying with their own time scale. They all have their own effect on the magnetopause. It's not so simple as to just pick an hourly average solar wind variable. So as a result, there's still plenty of scatter in where I say I predicted the magnetopause, but there's a lot of scatter in where it really occurred compared to where you predicted. And we need more studies comparing simulations and observations, because right now we don't really know where the magnetopause is. We think we do, but we don't. What about the magnetopause and reconnection? Basic questions you might ask are, where does reconnection occur? How does it occur? What are its spatiotemporal properties? A lot of people in the olden days, and I'm an old timer, talked about the component reconnection model. And there was another model called anti-parallel. And now a model which seems to do the best job is kind of a mixture of the two, a little bit different principle, the maximum shear model, which tells on the magnetopause where you think reconnection should occur. There's some regions where the fields are anti-parallel, maximum shear. They're also connected by a line passing through local nodes. So maybe everybody had something a little bit right. This model has been advocated very successfully by Karl-Heinz Trattner at numerous GEM meetings. We cannot omit to mention the pioneering work that MMS is doing on reconnection microphysics with a guide field and without a guide field, looking at the acceleration that occurs, the currents, fields, the types of electron phase-space density distributions that occur. Very detailed work helping us to understand this microphysics process which governs the overall interaction. Now, reconnection could be steady or unsteady. Here's a paper which said it was steady for hours, and they deduced that, Harold Frey and Tai Fan, by looking at remote images of the cusp dayside aurora and seeing a cusp auroral spot that stayed present and at a similar latitude and longitude for many hours at a time. So reconnection could be steady and balanced. Whoops, go forward. Of course, we also have reasons to believe it's unsteady. The IMF orientation is always changing, and we know a southward IMF will turn on reconnection and erode the magnetopause. Some people believe that each individual southward IMF turning triggers a burst of reconnection. That viewpoint was advocated by Lockwood many years ago. Other people can't find the triggers, but they can find the transient response, and therefore they conclude that there are no triggers. Reconnection is intrinsic. It's intrinsically unsteady at the magnetopause. One possibility is that turbulence in the magnetosheath triggers reconnection. Here is a global hybrid run by Nick O'Meady, where he keeps all the turbulence and he sees lots of FTEs. Here's one where he takes an eraser and rubs out the turbulence, only one FTE at the same time in the simulation. So maybe lots of little individual turbulence and wiggles and waves were triggering bursty reconnection localized at the magnetopause, maybe. But here's a simulation from Jimmy Rader, no turbulence in this global MHD simulation, and yet there are transient events, flux transfer events, bursts of reconnection that occur periodically in this simulation. You don't have to have turbulence to trigger reconnection. How big are these flux transfer events, and what is their topology? It's an open question. Here's the original picture of a flux rope with a dimension of about an Earth radii. Maybe it's a true flux rope with many Earth radii, or maybe it's a bubble extending over many Earth radii. Lots of possibilities. How long indeed is the reconnection line? Here is a deduction based on two dawn side observations of a reconnection line that occurs from the night side all the way to the subsolar point. That, of course, is an extrapolation. We unfortunately, at the present time, don't have multi-point observations capable of telling us where and when the reconnection extends, although people have used ground-based and space-based measurements. Zoo, for example, has worked on this problem. It's an open area of research. How big is a reconnection line? Do reconnection lines grow with time? In this early work by Lockwood, it was assumed that a reconnection line could appear suddenly over 4 hours or more in local time and produce an event just like that by snapping your fingers. Other papers like this one by Steve Milan attribute reconnection to some process that grows along the magnetopause, along the auroral oval, and continues after an initial burst. Maybe. Why would a reconnection line grow? Well, perhaps because some IMF discontinuity is coming in, touching off reconnection, and as the discontinuity moves to touch other parts of the magnetopause, reconnection spreads, maybe. Or maybe it grows at some alphane speed that propagates away from some initial disturbance. Or maybe it spreads at the speed of current carriers like ions and electrons. This is another hot topic of research pioneered by Zhu and co-workers. In any case, reconnection erodes the magnetopause. We all know that the dayside magnetopause moves inward when the IMF turns southward. We could ask the question, well, how fast? How fast does it move in following a southward IMF turning? Well, if reconnection were on the dayside were balanced by that in the magnetotail, the magnetopause wouldn't even move inward at all because all the flux eroded would be immediately replaced. But if it isn't immediately replaced, the magnetopause might move in very quickly. Dayside magnetopause moves closer to Earth quickly or slowly, or it might move in steps, each step being the removal of flux by 1 FTE. What do global MHD simulations tell us? Well, I've only looked at one, and in this simulation, the magnetopause following the onset of a southward IMF turning first moved in quickly and then more slowly. And then the inward motion came to a complete halt because a substorm occurred on the night side and pushed a whole bunch of flux back to the day side and pushed the magnetopause back almost to where it started. I don't know if that's typical or not. And those timescales are right. It's an open area of research. My favorite picture in this talk, Kelvin-Helmholtz waves. Surprisingly far more prevalent than anyone would have thought. And here they are, ripples on the flanks of the magnetosphere, ripples that Cavosi and Rader reported were present far more often than anyone would have thought, almost always. Down to the cusps. Why should we study the cusps? They're a pathway for solar wind energy to enter the magnetosphere. They help us learn about reconnection physics. They have plenty of transients in them. In steady state, we've got a pretty good grasp on where they occur, and the transients, there are lots more to be learned there. So where is the low altitude cusp? From statistical studies, for example, of DMSP, we know that the cusps are within 2 hours of local noon at about 78 degrees magnetic latitude. Here's some more statistics on them about your probability of seeing them as a function of local time here on the left, the latitude that they occur at as a function of IMFBZ, their latitudinal range, a couple of degrees, 1 or 2 degrees. Big statistical studies, plenty of data to execute them, high confidence. Let's see if we can go on. Whoops. We also have a pretty good idea about densities in the cusp. They track those in the solar wind, so that's good because the plasma in the cusp should come from the solar wind. Spectacular study by Benoit Leroux of cusp plasma parameters on the basis of cluster observations. He also did magnetic field parameters there. You can see the plasma there, and in his study you can see where it's accelerated and which way it's going and how it's penetrating. Cusp moves equatorward following southward IMF turnings. Got it. Here are 3 cluster spacecraft observations of the cusp at successive times. Clearly the cusp moved from high latitudes to low latitudes. So things change in the cusp as a function of time. They might also be spatial. What do we not know about the cusp? We don't have any instantaneous global picture. We don't know whether reconnection occurs at single or multiple locations, and we're not sure whether reconnection is steady or unsteady. Here are some cartoon predictions for cusp density and emission structures from Weiss, 1995. Various IMF conditions, reconnection occurring at 1 or more locations, creating structures that extend in azimuth and latitude, might be diagnostic. If you could take pictures of the cusp and see these, we want to take pictures of the cusp. We want to distinguish between different models for time-dependent and spatial structure in the cusp. And the good news is we're in about to be able to do that. The Cupid CubeSat will launch this September. It will look upward into the cusp and take snapshots of the density structures there in soft X-rays emitted by solar wind, high charge state solar wind ions interacting with exospheric neutrals. That's the remote sensing or optical mission that's coming up. But there's also an in situ mission coming up. That is the tracers mission. 2 spacecraft will fly through the cusp, one after the other, checking out whether there are spatial or temporal structures there. Gonna be cool. The future for cusp studies is wonderful. So last topic, Dayside High Latitude ionosphere. Why study this? We can use ground-based measurements in the high latitude ionosphere to study solar wind entry into the magnetosphere. It's a great place to remotely study reconnection physics and transients in the solar wind magnetosphere interaction. We have a whole array of observatories there, which include ground radar, magnetometer, rheometer, and all sky imagers that can help us reach our conclusions. There are lots of cool transients. I just have one slide. I'd like to mention that for me and for GEM, this is where GEM began. One of the first campaigns at GEM was to look at ground-based observations and deduce the nature of the solar wind magnetosphere interaction from them. On the left, you see how magnetometer observations can be combined to deduce traveling convection vortices. Perhaps they're due to pressure pulses. Perhaps they're due to the Kelvin-Helmholtz instability. Perhaps they're due to flux transfer events. Whoops. Oh, let's go back. All sky imagers, really cool features. There's a wealth of information in all sky imagers, far more I know from talking to Briggs, who was a summer student at Goddard, far more than have been reported in the literature. Very wealthy data set, full of interesting events. Super Darwin ground radar showing FTEs moving up into the realm of endeavor with much more work to be done. So that brings me to the last slide. What is the future for Dayside interactions? Well, there certainly are more questions than there are answers, and that's a wonderful thing. It's a vibrant area of research. We're entering a time when global MHD and hybrid code models are going to be available at your request. That is going to make it spectacularly exciting because they will make predictions that observational people will test, and they will go out to see if they can simulate what observers report. The role of the exosphere is becoming more clear and more important. We've got a forthcoming mission, another mission coming up, the GLIDE mission, which is specifically going to tell us the properties of the exosphere from an L1 vantage point. Pay attention to that interesting mission. We've got these two Cusp missions coming up, Cupid and Tracers, that are going to define the nature of reconnection, one by remote sensing, one by in situ measurements. The existing missions like Cluster Themis and MMS, their orbits continue to evolve. There's new configurations that will help us better determine the properties of the outer magnetosphere. There's an opportunity for future missions to construct constellations and have multi-point simultaneous measurements that would likely employ CubeSats. There are immense prospects for global imaging in EUV, FUV, ENA, Lyman alpha, Thomson scattering, and soft X-rays to look at the plasma structures that are out there. So it's really a wonderful time to come. And last, I'd like to mention a recent review on this topic, Dayside Magnetosphere Interactions, an AGU monograph by Zhong and Zhang, which came out last year. And that's it. Happy to hear any questions.
Thank you, Dr. Sibeck. That was a fantastic talk. We've got a few questions in the Q&A. We'll start just with the ones that are here at the top. So from Drew Turner, what are the integration times and spatial resolution for soft X-ray imaging of the magnetopause and sheath? And how much is the magnetopause expected to move during those integrations? Okay. What about line of sight projection effects?
Okay, so first topic, a notional or nominal integration time for a soft X-ray imager of the magnetopause and magnetosheath, for example, 30 Earth radii from the Earth, would be about 2 minutes. But in general, soft X-ray imagers like that on Cupid or the one on SMILE return individual counts. So on days when more X-rays are generated, i.e. days when the solar wind flux is higher, then the integration time can be less, perhaps even as small as 15 seconds. So the bigger the solar wind disturbance, the shorter the integration time, and or the better the spatial resolution with which you construct pixels. There are line of sight effects, and the interesting thing is that the dominant source of X-rays along a line of sight comes from the tangent to the magnetopause, because that is the closest approach to the Earth, the deepest position within the exosphere, and the place where the neutral densities are highest. And that is therefore dominates the entire line of sight. And the amount the magnetopause moves, magnetopause motion, you probably would not want to you might not want to try to track Kelvin-Helmholtz waves on the magnetopause, because you might have tens or hundreds of kilometers per second magnetopause velocity, but 10 kilometers per second or 20 kilometers per second when you're trying to find spatial features that are 1/8 of an RE or 1/4 of an RE, that's not going to make too much trouble for that.
All right, moving on. Next question's from Michael Hardinger. Hi, David. Do you think we'll ever get to a point where we can predict, even roughly, large magnetopause perturbations caused by foreshock disturbances, similar to what can be done for IP shocks with L1 data and numerical simulations? Could this be done with imaging, remote sensing, L1 data, etc.?
Well, first of all, it's my personal belief that using L1 data, I've seen so many cases with a lack of success of what came to the magnetosphere, that an in situ L1 monitor is never going to be 100% and may not even be anywhere close to 100% in predicting these big disturbances. On the other hand, we can't simply put a spacecraft at x equals 30 of the magnetosphere and leave it there. It won't stay there. So we can't do that either. If we went to imaging, we could image what's coming in, but then that wouldn't be so much, I mean, image in the solar wind looking from the side or the magnetopause, but then that would be a nowcast rather than a forecast. We'd be seeing the big change as it happens. So I think there are always going to be rogue events that we couldn't predict going on.
Okay, and then we've got another follow-up on that. Considering the importance of space weather and solar wind driving of the magnetosphere, ionosphere, thermosphere system, do we need a dedicated solar wind monitor inside of L1, for example, at the cislunar space?
Okay, so let's go back, let's ponder the slides I showed. If your objective is to predict a substorm or a geomagnetic storm, you can do pretty well with the hourly averages upstream. The correlations were not too bad for that. You'll miss some of them. But if you're interested in transient events, then the situation is a lot tougher. But to put a monitor well, okay, so what you could do is you could have a lot of spacecraft up there, a constellation of maybe 3, 4, 5 going around a circle around the Earth at 30 RE. Imagine having 5 IMP-8 spacecraft at distances of 30 to 40 RE, so that one of them was always upstream. If you truly thought that transient events were important and triggers for the solar wind interaction, that would probably be the way you'd approach it. They would take turns, each one of them taking turn as a sentinel as they go around the Earth.
Okay, and then we also have a live question from the audience. Joaquin Byrne, I believe. I think we're going to get their mic unmuted so they can ask directly.
Okay, super.
Yep, you should be able to unmute now and talk.
Joachim, are you there?
Sorry, that was me. I think I just pressed it by mistake.
Well, I'm glad to hear from you anyways.
Yeah, so glad to see you. So very nice talk.
Thank you.
Well, then we'll go back to the Q&A. We've got a question here from Bill Latko. For quasi-steady IMF solar wind conditions, does the transient nature of reconnection or its degree of transience depend on IMF orientation?
I don't know the answer to that. That's an open question. I'm going to try to repeat that question back to make sure I understood it. If the IMF is steady, is there a preferred orientation for transients to occur? Certainly a steady northward, we're not going to see much happening on the Dayside equatorial magnetopause. A steady southward, we are likely to see lots of FTEs, which someone might claim is due to an intrinsic instability, and someone else might look for small fluctuations in the southward IMF to see, or turbulence generated. So I think there's room for a lot more work on that subject.
Okay, I think we've got time for one more question from Jason Durr. Absolutely love the talk. Are there any general pedagogical comments you have about how the variation in magnetopause boundary location in response to solar wind pressure affects the predictive utility of L1 orbit measurements?
Oh, I've got to think my way through those words. Well, could you repeat that question again?
Sure. Are there any general comments you have about how the variation in magnetopause boundary location in response to the solar wind pressure affects the predictive utility of L1 orbit measurements?
I think my short answer is no. I think this is an open area of investigation that someone should take the big list of crossings that we have right now, the various global models that we have, the solar wind input from different L1 monitors, and see just how well we can do. And I've talked to Jari Collado-Veda, who works at Goddard in the CCMC, and it's not a very pretty story, and we're not that successful. Sure, everyone agrees the southward turning erodes the magnetopause. Everyone agrees a pressure increase moves it in, but exactly where it is, there's considerable disagreement between models and observations. And that might be because we're missing some of the control parameters. It might be because the models need a bit more work. It might be because the upstream monitor's in the wrong place and not doing it. And it might be this idea that I can bin everything by hourly averages of solar wind parameters. Maybe that's wrong. Some things respond quicker than an hour. Some things take more than an hour. There's a lot of work to be done there.
Okay. I think we've got a little more time, so we'll ask another. This is from Manhua. Hi, David. Thanks very much for the great talk. Could you please comment on particle heating by waves in the sheath? I'm especially curious whether mirror mode waves can accelerate particles. As a follow-up, are there any waves that can accelerate both ions and electrons in the sheath?
Okay, so by chance, I have come across recently some papers from the cluster mission which show electrons heated to superthermal energies, not astronomically large energies, in mirror mode waves. And if you send me an email, I'll look for the references to those. But that's not energizing them to tens of keV. That's just getting them above the thermal level, and they're in each and every pocket of the waves. And probably the same thing is true for ions too. And the latter part of the question was what?
Are there any waves that can accelerate both ions and electrons in the sheath?
I think there's at least some degree of acceleration by the mirror mode waves of both, but not usually those accelerated particles are attributed to processes at the shock and then convection downstream into the sheath to higher energies.
All right. This is the last question in the chat, but we're still waiting for a panelist. So if anyone in the audience wants to add additional questions, we'll welcome them. But for now, Rebecca asks, can you please comment on the energy distribution of the accelerated ions in the foreshock? Could it be confused with an astrophysical plasma of a similar temperature, or is the energy spread too wide?
Oh, okay. So I would love to talk a little more about this topic. First of all, if you're sitting upstream from the bow shock, you could be in the middle of a solar energetic particle event, and then that distribution of particles goes to much higher energies than can be produced at the bow shock. And so your bow shock generated particles could be superimposed on it, but they have their own spectrum, and they only get up perhaps to 1 MeV for ions and several hundred keV for electrons. They're not coming from another astrophysical source unless they're cosmic rays, and then their energies are even higher. But I do want to mention, in recent years, there's been some continued work going on simple leakage from the magnetosphere. Sometimes you see O+ or He+ ions, and they have succeeded in swimming against the turbulence in the sheath and crossed the bow shock and gotten into the upstream region. And they may be more common than most of us thought until recently. And the way that they are identified is on the basis of composition. If you have an instrument that can actually see O+, that's a good indicator of something that came from the magnetosphere, because the solar wind itself is O6+ or O7+ or O5+. So in short, with experience, you can readily look at upstream events, see that they occur on magnetic field lines connected to the bow shock, see the corresponding waves or turbulence that help generate them, see their spectrum, and see that it's limited to some hundreds of keV or MeV, rule out that they're a solar energetic particle event, and use composition to rule out that they came from the magnetosphere.
All right, thank you. I don't see any other questions in the Q&A, and no one has their hand raised, but we do have one in the chat from Vanya. As a former steering committee chair, what would you consider, or what do you see, what's your vision for the future of GEM?
Oh, okay. I have a few comments. One is originally GEM was predicated on a heavy use of NSF supported resources. And that's why one of the first campaigns was on the high latitude Dayside ionosphere. And so I would like to see stronger participation and presence by those making use of ground-based observations, which are an NSF resource. I'd like to see the NSF make a bigger deal out of that to support the financial viability of those ground-based programs. A second topic that concerns me, and concerned me even when I was chair of GEM, and I did not find a good solution, was the ensuring that the GEM would not be a summer-fall AGU. Rather, the emphasis should be on discussion, and people should at all possibilities should be encouraged to discuss work that is not yet completed in an atmosphere where they could be confident that that's acceptable to do that. And that new ideas, the balance between discussion and formalized presentations, I got more out of the discussion type activities. Of that for me is one of the highlights of my GEM career, is informal discussions inside and outside meeting rooms on problems that are not yet solved, on topics where I actually can have a say and influence the course of events, or learn something, or go off and develop new partnerships. But yesterday there was a session on what GEM means to me, and I have to say GEM has been my entire career. I've been there from the start, 30 years, and it's the highlight of my year, and it is the place where I have made the most lasting friendships and partnerships in my career. So I'll put that in as something that gives me a warm, happy feeling.
Fantastic, thank you. I think we've got one last question from Michael Hardinger. I see your hand raised. You should be able to unmute now, and that will be our last question to David for today.
Okay, great. Hopefully you can hear me. Fantastic talk, David. I really enjoyed it. Great information. Just to follow up on the question I had earlier about predicting and the rogue event comment you mentioned, that will never capture these. I'm just wondering, with the current modeling capabilities, like the hybrid kinetic models, if you can really well prescribe the pressure and the IMF and everything at like 30 RE, like let's say you had 30 satellites up there, and you could prescribe it everywhere along like a 30 RE boundary.
Yeah.
Is there still an element of random chance? Like, do you think you would still miss some events? Could you comment on that?
First of all, our models are almost at the level where they can be put to the use you want. The closest I've seen is a 3-dimensional model from Yulin. The Vlasiator model is 2D, 2.5D. The Nicomedes model, 2.5D. So we're just on the edge of even having models to do 3-dimensional global interactions. I think that it's not an element of chance, but you would probably have to have an inter-spacecraft separation of like 20 or 15 RE along a circular path around the Earth, because some of these an edge might not come to Earth, and so you'd have to have a spacecraft at 30 RE from Earth that's within 10 or 15 or 20 RE from the Sun-Earth line to even be reasonably 100% sure that was going to come to Earth.
All right, thank you. I will turn the mic back over to Adam, and we'll continue with our next plenary speaker.
Thanks, everybody.
Yeah, thank you, Dave.